This webinar today is very much a passion project, and it's not the heading there that I needed to change, but our agenda is definition of test uncertainty ratio. Some people get that confused with test accuracy ratio. We're hoping to clear the air. How to calculate TUR. We've done webinars in the past about probability of false accept, analyzing location of the measurement, but kind of going a little bit back to basics on let's break apart the formula. It's basic math, and let's make sure everybody's calculating TUR properly. Using TUR with the location of the measurement, CPK. I'm going to show a lot of new stuff regarding CPK. For those that are in testing, they may recognize this term. It's Process Capability Index. I'm going to talk more about that later. And the effect of the UT resolution and risk. That's, again, I don't need to say more about that. Outcomes. If you're on this call, hopefully you have a desire to learn what is this TUR, how do I calculate TUR? There aren't that many reference documents out there for this. We did create it for the metrology handbook that Heather's absolutely helped me with, and her contributions are greatly appreciated there. So we did do it that. The metrology handbook's not out yet, so we want to get as many people as we can help. We want to do that. And we also want best practices. I mean, we're talking about an ANSI NCSLI Z540.3 document, ILAC P14, and ISO IEC 17025-2017. Some people may say, why are you talking about a withdrawn document? And I'll tell you, because it has the best definition of TUR. Otherwise, you have to kind of infer the definition from ILAC P14, which is clear, but not nearly as clear as Z540.3. So let's discuss that when we break into sections of standards. This has been a hot topic. It was around, right? Conformity assessment was around in the 2005 standard. It was section 510, I believe. I lose track of all the numbers. You get older and your brain retains information that sometimes you don't want it to retain and others not. But I believe it was 510, the section that talked about compliance, I believe was in the 2005 standard. And now it's conformity. We're still evaluating risk, but this threw a lot of people for a headache. And this section says the laboratory shall document the decision rule employed, taking into account the level of risk such as false accept and false reject, and statistical assumptions associated with the rule. Now, this threw everybody for a loop. They're like, decision rules? Why do we have to do all the decision rules? Is it simple accept? Is it others? We should do a webinar on decision rules. We've done them, but the more I learn, wrote a chapter in the metrology handbook, the more I learn, my opinions seem to change. And for everybody out there listening, it's kind of hard to discuss this, but I think you know what I'm talking about, is what we say today is our truth. But as we learn more, that truth changes. So past classes I've taught on decision rules and everything else, I think the metrology handbook is good because I've tried to approach it from a really non-biased perspective. And let's just lay out some framework. However, now the more I think about it, I'm really leaning and liking this CPK concept a lot that we're going to talk about. I think there is one rule to rule them all, and we can talk about that. But TUR is a foundational piece, right? It's crucial because it is commonly accepted practice in making a statement of conformity. We have documents like JCGM 106. We have ASME documents. We have a lot of other that reference TUR. Right? And then when used in the combination with the measurement location, one can calculate measurement risk at the time of calibration. And then it's clearly defined in these ANSI NCSLI standards. So that's why I keep them around. Part of the problem is accreditation bodies recommend requirements on contributors to measurement uncertainty should be considered by the end user to aid in calculating the optimal TUR. One may argue that the reference standard and certain environmental factors are the only requirements needed to calculate TUR to make conformity assessment decision. That's really what we're talking about. Make no mistake, it is clearly defined and was agreed upon back in 2006. There are no standard committees writing, hey, TUR, don't take the resolution into account, just use this. We're hopefully gonna put that to rest, give a proper definition, and then hopefully people can go use it. And the definition of CPU, which is calibration process uncertainty. I hate when people use acronyms and do not tell you what they mean. It's another peeve. If I see CPU, MU, MT&E, and everybody gets all confused, MPU, MPE, maximum permissible error, and eventually you get lost. It's kind of like the kids that are texting. I don't need a dictionary to understand things, but when my kids started saying fire, I was like, where is this coming from? But I knew that was hot, and it's just stupid stuff. But anyway, CPU is calibration process uncertainty. It establishes whether relevant uncertainty contributors to the customer's device will be considered by the calibration laboratory that is calibrating the equipment. If a calibration laboratory does not include these uncertainty contributors, then they are passing the risk to the customer or consumer because the laboratory prefers not to retain the risk. This is often done without the end user's knowledge. There is a lot of text on this slide. And what ends up happening, and I will paint the picture, it is not going to be 100% accurate for everyone, and as nothing is. But what typically ends up happening, someone says, I need a calibration. Someone goes and shops on well, who can do it? Go to Google, go to whatever. Who can do X? So purchasing officer, someone else says, great, I found this company. They can calibrate it. Reach out to the company, get a price. Maybe reach out to 2 other companies, get a price. What often does not always happen is they do not evaluate the scope, right? How good is that measurement? And now here I'm detouring because I know I had it set up beforehand. So if we go to accreditation, how good is this scope? Right here, we're both NavLab and A2LA, accredited by NavLab and A2LA. Let's go to the NavLab scope. I go to the A2LA scope all the time. Let's go to NavLab. So I need someone to do a calibration. How good are they? Well, here I go to Morehouse. I'm biased because that's us, right? I go and say, oh, they can do force to 003 to 105 grams. They can do, oh, wow, look at these numbers, 0016, 016. Then they go, here's using force transducers, here's aircraft scales. As Heather said, torque, 003 when we do accreditation requirements. So these numbers are really, really low. When you think about 16 parts per million, 0.0016, that's going to, and I'll show people later, that's going to allow us to make more conformity assessments, to say more devices are in tolerance when we consider actually the impact of measurement uncertainty. But what ends up happening is the buyer just doesn't shop for that. They shop on who can do it. So everybody has different uncertainties, and some people can calibrate your devices and some people cannot. If the person's in purchasing, again, that scenario, maybe they don't know, and you might not be getting what you really need. And then we further go out to say, hey, not only might you not be getting what you may not need, that lab might give you conformity assessment based on manufacturer's tolerance. And if they do that, that is a situation of shared risk, which I'll come back to, which is not good for you. A lot of times that is not good for you because if it's shared risk, that means up to 50% of the, you could absorb up to 50% of the risk. So ANSI C540.3, kind of coming back, detoured a little bit. ANSI C540 requirements for calibration and measuring test equipment. Allows for test uncertainty ratio equal to or greater than 4:1 when it is not practical to estimate the false accept risk. Then goes to say objective evidence of non-practical. Here's where we get into these things like 4:1 TUR and everything else. So I'm going to show people something, and I was debating today when to do it, but I'm going to do it now because it's fresh in my head. So I'm going to show people something. And if you look at this, before we get into the calculation of TUR, if you look at this sheet, and I just want you to look at this, K equals 1, right, TUR of 1:1, And this is, if we look at it, this is from my good friend Greg Senker at NDSoft. Give a shout out to him. This is the percent of spec max you can test to while still being below 2% PFA. What this table is really saying is if I have a 1-to-1 TUR, I have the smallest bit of range determined as far as that location of the measurement. I need to be darn near close to nominal or it's not going to work. And then this is giving you these ratios. They will work almost with any number on the TUR. So as your TUR goes up, look what happens to my percentage. So if I have a TUR, and the caveat is it needs to be calculated correctly. So if I have a TUR of 2-to-1, I have about 48.66% to be in spec. And then if I go up to this imaginary 4, we'll round up, right? If we're metrologists here, close your ears because you're going to have a problem with this statement. But in any case, instead of saying 74.33, we can say about 75% because it's easy for people to visualize. If I have a spec of plus or minus 10 pounds, if I have a 4-to-1 TUR, this is basically saying, about 75%, about 7.5 pounds are what I have to be within. I can't be within the plus or minus 10. Hopefully that'll come together later when we look at things. But I wanted to show people that because you don't always see it, right, on what this is. And here's some more information, as I said, going to this different spreadsheet, which we'll come back to later. But at a 3.1, and you can see the measured value versus max uncertainty curves. Anyway, I'm going to go back to this. I was debating on when to go to it, but I wanted to show people this so we can, hopefully you can visualize that, hey, if your TURs are low, or you go to that calibration supplier that has high uncertainties, and they give you if they give you a 1-to-1 TUR or whatever, chances of you being in spec, if they follow these formulas, are pretty low. So if we define that TUR, we have two definitions. One's ILAC G8, the other is ANSI NCSLI Z540.3, and it's the ratio of span of the tolerance of a measurement quantity subject to calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. Then we go to ILAC G8, the ratio of tolerance, a measured quantity divided by they're virtually saying they're very similar. However, the span of the tolerance in the numerator must be clearer in the ILAC G8 version. If the tolerance is not symmetrical, meaning plus or minus 10 on each side, right, up or lower, not symmetrical. If it's not symmetrical, then the ANSI NCSLI definition here is clearer. So it's something for the ILAC G8 folks to maybe clean up in a new revision. But ILAC G8's a fantastic document. ILAC P14, fantastic. I'm missing P14 and G8. G8 is a guidance document for conformity assessment. P14 is a policy document. So handbook here. This is the ANSI Z540. Talks about the numerator. People can read. You can get the slide deck. What I really, not a lot of people have issues with the span of tolerance. That's pretty easy what we see. But here's where the issue comes into play. And this is the most thorough definition of TUR. For the denominator, the 95% expanded uncertainty of the measurement used for calibrating, following calibration to use to calculate TUR. And here's what it says, right, and highlighted. Include influences of the item being calibrated except for the bias of the M&T. That's measuring and test equipment. Another, the calibration process error therefore includes temporary and non-correctable influences incurred during calibration, such as repeatability of the UUT. Now, talking around this, sometimes you won't get the repeatability of the UUT because it was used when the lab calibrated their CMC. They're calibrating a like device, and they can kind of substitute that in. But that gets on the edge of things too. Resolution is there, the resolution of the UT, and I'll show you why we have resolution later. And then the error in the measurement source, operator error and correction factors, and that's where we put the other. So if we look at this formula, CMC is the calibration and measurement capability. That's in our denominator here, right? That's calibration and measurement capability. That's basically what is on that accreditation certificate. For us, it was the 0.0016. The resolution is the resolution of what's being tested. Repeatability is what is being tested. That's this UUT. UUT is unit under test. Some people call it DUT. I'm all over the place. I've read so many documents and it's all over. I like unit under test. I have my own bias. Device under test, same thing. We can speak the same language, but just know that it's DUT or UUT, same things. Then we look at ILAC P14. That's our policy document. And it says basically the same thing, but not as clear, right? The uncertainty shall cover the same contributors to the uncertainty that were included in the evaluation of the CMC uncertainty component. Except that uncertainty components evaluated for the best existing device shall be replaced with those of the customer's device. Therefore, reported uncertainties tend to be larger than the uncertainty covered by the CMC. This is correct, right? Because when we're using the best existing device, things like resolution, maybe we have an indicator that'll read out to 6 decimals. We bought a super high-end one, and then the customer sent in a 5-decimal one. This is where resolution becomes that much more critical. And if you look at the definition, it's also why we need resolution, so we can't cheat, right? If I had since we're in force, if I had a 1,000-pound load cell and I read my 1,000-pound load cell by 0.1, just simple math here, right? That's 100,000 counts. Probably I'm going to see some variation in that number. However, if I was a manufacturer and I wanted a perfect instrument and resolution didn't matter, I would set my resolution to this, 1,000 counts. Chances of me seeing any variation at this digit in a dead weight machine, very, very low. So we can make perfect measurements the whole way up, 100, 200, 300. If we're not accounting for that resolution, we're not penalized at all. Why read it out to extra precision or decimals? It can be a perfect instrument. I applied 1,000 pounds and I know that I'm good to 1,000 pounds. Really wrong, and wrong on wrong in a lot of ways. But one of the biggest one is we're not accounting. If we do not account for the contribution of resolution, we're really we're not taking risk into account at all. We can just set things to be perfect. So I like the word art. You go in, you play with word art, but here's some of the things it's just a slide to refresh, right? About how ILAC P14 addresses the UUT's resolution needs to be included and what should be included in the expanded uncertainty, repeatability, resolution, error and conversion factors, short-term contributors, operator error. All of these things should be included in that. We get to the actual, let's apply the definition. So one of our customers sends us a 10,000-pound load cell with an accuracy specification of plus or minus 0.05% of full scale. We plan on using a Morehouse UCM to perform the calibration. When 10,000 pounds is applied, the unit reads 10,001. So the display reads 1. That is 1 pound. So we have 10,000 counts of resolution. This is pretty coarse. I would like for somebody to have more resolution, but this is typically trying to say what people might see more of, and that's always hard when we go out and teach and all kinds of scenarios. So if we're doing it, calculate the numerator, right? And the device is 10,000 pounds with an accuracy of 0.05. What does that mean? Well, that means if we take 10,000 pounds here and we multiply it by, if we multiply by percent, 0.05 becomes 0.005, which means plus or minus 5 pounds with a 1 pound resolution. Here, I'll fix this right now. Heather's not watching. So this means the upper specification limit will be 10,005, 10,000 plus 5, and the lower specification limit will be 9,995 or 10,000 minus 5. That's all we're doing. We're subtracting, we're adding and subtracting, right? Thus we have this, right? 10,005 minus 995. So the numerator, the span of the tolerance, is 10 pounds. Hopefully that's really simple. It's simple math, and you can go over it, and I'll fix the spelling error for anybody that requests the slide deck. Now we get into the more complex part, and that's calculating the denominator, reducing everything to one standard deviation. CMC is the uncertainty at the calibrated force. If we used our UCM, we achieved an uncertainty at O2 at 10,000. This is a believable number. We're not at dead weight at 0016. Again, a lot of people are using the secondary standards and whatnot. O2 is a very good number. That's how good we are. And so if we use this, we say, hey, so if I'm O2 at 10,000, what does this become? Well, it's 10,000 times O2. So I'm checking off the CMC part here. We would then reduce to the standard uncertainty by dividing by the in most cases. This is, a lot of people do this. I'm going to show a little bit more about it later. But most case, people assume the coverage factor is 2. On all of our equipment, we can correct to make it 2, or you get a number and we just round up. You do enough, your sample size is long enough that you just say, hey, I used an equation and it's 1.98, I'm rounding up to 2. But in any case, a good number is typically, or the assumed number is 2. In this case, the divisor is 2. The appropriate divisor should be listed on the certificate. So we've really done, all we've done is this. We said, okay, the CMC component is this. Now our next one, we need to go figure out this resolution. Resolution was really interesting for force easy ways to calculate resolution. And there's what we're doing. This works on almost anything. Divide by the output at capacity and multiply by readability. In fact, I haven't found one instance where it breaks. So at 10,000 reading by 1, it's pretty easy to know it's 1. But if you had 4.4 millivolts, right? And I can do this quick math for people. 10,000 divided by 4 is what? So if I had a 4 millivolt cell at my output, that's 2,500. Well, that's not my resolution. It's my resolution per millivolt. But then if I multiply that by the readability, if this would read by 0.00001, right? Now I would have a quarter pound would be my resolution if I had a 4 millivolt cell. So this formula works. It's in the sheet. I've kind of butchered it with I'm trying to write with a mouse and not a pen, so that's why it looks so atrocious. But the formula works. In this example, we are using 1 pound. It's very, very easy, but you can use that formula for any, if you want to calculate resolution, you can use it for any device. So 1 pound, little bit of trickiness here. Snuck in this square root of 12. This comes from M3003, which basically says a resolution would assume a rectangular distribution, but since we have an equal probability, if I draw this out, right, and I have M3003, and sorry for my bad sketch. So if I have a digital instrument that's 1 pound, half of my readings are going to be between what, 0.1, the imaginary digit on my indicator is going to be between 0.1 and 0.4, and over here between 0.5 and 0.9. So between this imaginary digit, we do not know where it's going to fall, and therefore I have two-sided probability, and I drew this intentionally, but it's not a perfect rectangle. So each one of these is the square root of 3. And since I do not know where it is going to fall, if I take 2 times the square root of 3, I actually get the square root of 12. This is why you see resolution as the square root of 12, or 3.464. So that takes care of the second stage in calculating TUR. Now, repeatability. How well does the unit repeat in the test scenario? This is where it gets a bit of, it's where it gets a little bit tricky. One can remove the repeatability contribution to the CMC above and substitute the repeatability of what they are calibrating if the device represents that of a similar device used to calculate the CMC. They can decide not to do repeatability on the instrument submitted for calibration. So if somebody sends us a load cell and I've already done CMC calculations and repeatability in my machine and everything else, I've done 5, 10, I assume I've tested R&R between my operators. I can assume my process is pretty good, and I've taken into account all the uncertainty contributors. And maybe someone sends us a very similar device as we use to calculate the CMC, then we can just say, hey, we know this is repeatable, and chances are this is going to be the biggest impact right here on the resolution. But if we don't know that, it's always good to take repeatability numbers. The problem is taking them costs more. Customers don't always want to pay, nor should they. I mean, it's all about evaluating the appropriate level of risk for your application. And we've come up with so many creative solutions for customers just to make sure their risk and needs are being met. So we do all kinds of things. But to obtain repeatability, we apply 10,000 pounds to the unit under test because that's our test point that we were testing. We do that 5 times, take the standard deviation. In Excel, you can use this function equals standard deviation. So if I took 5 measurements, 10,000, 10,001, 10,000, and I take the standard deviation of those measurements, you'll get 0.54772. And that goes in here. Now, other error sources could be, typically we don't know these. These are usually set to 0, but if you know them, you can put them in. They can be things like environmental influences, correction factors. This is a discussion with the customer that says, hey, I use this or I don't use this. But for this example, we're going to assume the calibration was calculated correctly. That's, I can tell you, we typically do not use the U other. It's there in case a scenario comes up or you know it. We rarely see it. Our temperature is controlled within a ½ degree C. Humidity is good. Everything else, we're doing it, we have thermometers galore. We have 5 remote ones that we're doing tracking, SPC tracking and everything else. And then we have really good, those are accurate, I believe, to 0.1 degree. And then we have some hearts that's later bought by Fluke that are good to about 0.01, better than 0.01. So we're monitoring our temperature, and I can tell you that it really does not change by more than a couple tenths of a degree during any cal. And our lab maintains a consistent temperature within plus or minus about a ½ degree. Requirement for most labs is 1 degree C. So moving on with this, we reduce the denominator. We can use Excel. Be careful with Excel. This was one that got me. I woke up one of the nights and sometimes I can't sleep and I don't know why I can't sleep. And I'm like, did I do everything right? Something's wrong. I'm double checking everything. So the parentheses in Excel are very important. If someone types these in and gets this wrong, you will probably not get this answer. So you need to be very careful with Excel. I've done it numerous times where I've just created something for someone else. And then I go back and I use a test case and I'm like, why am I not getting the answer I want to get? And it's usually I have a paren wrong or I'm up at 3 a.m. or something like that where it's just not, it's not jiving because I made some mistake. So what I've learned is to double check everything. Or better yet, if you have these formulas, just take them from sheets you previously made that have been validated, revalidate, and make sure. But here it is in Excel, easy to program. So now we have TUR over 2 times the 95% confidence. At the end of this, we take our specification of 10, divide it by 2 at 95% process uncertainty, which we're using 2 for. So we have 10 divided by this number, and that becomes 10 divided by this. This can, to confuse people, don't mean to, but you'll get the same number if you took half this and divide it by this. But anyway, I prefer to write it out. We have 10 divided by 2 times K equals 95%. And therefore, we have effectively shown, again, I think people are going to want the workbook and want to use some Excel functions. I encourage everyone to start, just build this formula out in Excel, play with it, do what you want. Right now, we have a TUR of 2.125. Now, validation, right? You can do this by hand. It's not that difficult. But if we do this in Excel, like I said, validation is key. Resolution is this. Repeatability is this. The standard, the sum of the squares is this. Square root of the sum of the squares. Little u, that's K equals 1. Multiplied by our coverage factor, that's K equals 2. Tolerance is this. Tolerance divided by 2 is 5. TUR, remember I said it's the same thing. You can divide by 5 or you can do this. That should be the exact same answer we got. So it's 2.125572, 2.1256. We rounded the 5572 to the 0.6. At some point, you're going to make rounding. You determine standards say to two significant figures. It's up to you to decide. Really, if I was rounding, I'd probably call this 2.13. We do all that. It's how it's calculated. And then once we do it, we can build cool tools in Excel and everything else. Here you can see, here's the same scenario, upper specification, what we just covered, already built for Excel. This is online. You can go download it. It's called a PFA worksheet. It is unprotected. It's in the documents and tools section of the website. You can play with it all you want. Here, $9.95. We didn't come up with this, though. We just said, hey, upper, lower, measurement error, standard uncertainty. I typed in the repeatability numbers. I typed in everything else. They're on the sheet. So, yep, TUR made it real long. TAR, that's that dreaded word I hate. This really never changes. That's test accuracy ratio. I put it in there to demonstrate. You could start looking at things when you do not take measurement uncertainty into account, when you do not do other things. It's typically TAR is going to be a constant because you're not using resolution, you're not using repeatability. And then this pesky little CPK thing, and that detects the location of the measurement, which I'm going to talk more about. So when I substitute all of this in, right, my spec plus or minus 5 pounds, TUR of 2.12, and I look at my total risk and do this graphically. This is done by a normal distribution function. And do this graphically. My risk is 0.03. If the goal is to be less than 2%, which is required by most standards, we're in. We can make a conformance assessment. So if you see this down here, I like putting this on all the sheets. If we just do a general subtraction of uncertainty, it basically is saying with a TUR of 2.12557 to 1, that if I just subtract uncertainty, that 9997.35 and 10,000.2, if my device is within this, I could make conformity. If I need to go to 2%, you see that limit changes a little bit. We're at 416 and 584. So we lost effectively here. We didn't really lose anything because our instrument's only reading by 1. If we were reading by 0.1, we would have lost, but it just depends. It can round up or round down. In both of these cases, it's 997 to 10,002. But we'll look at that. Sample size, talked about it. In this example, we're using the sample standard deviation of 5 measurements. Want to tell everybody that we want to be careful multiplying everything by the coverage factor to ensure 95% confidence. To do so correctly, we may want to calculate the appropriate degrees of freedom. Now we're getting into more advanced stuff. If you get to this point and have TUR right, I'm going to make a blanket statement that I'm using the REM method, that's rectal extraction method, that you are going to be ahead of a lot. You're going to be ahead of what I consider a lot of laboratories, because more and more, the reason we're doing this is because we see people doing it wrong all the time. And since we see a trend, we want to try to correct that trend. So I'm so thrilled that you're on this call. But if you start doing it, you're going to be ahead of a lot of people. Not all of them, but a lot. This whole concept that I'm getting into of sample sizes covered a lot more detail in expanded uncertainty classes talking about degrees of freedom. But it's another topic I think people should be aware of. Here's generally, this is an uncertainty worksheet. It corrects for students T. It does a lot of stuff, and it might be some people may recognize the Welch-Satterthwaite equations. Other ones, this might be like someone just turned a fire hose on and asked you to take a drink. So if we look at this, what I wanted to show people is focus. If we just multiply everything by 2 versus using this, JCGM recommends this method where you calculate the degrees of the effective degrees of freedom and whatnot. So this basically says, hey, I took 5 measurements. These are my inputs: repeatability, reference standard uncertainty, resolution on the device. We should add environmental, everything else. This is just pretty much down and dirty on the TUR calculation. So if I multiplied everything by 2, not much difference, 0.09, but I took 5 measurements. Now I'm taking 3 measurements, which means I have degrees of freedom is 2. It's basically n minus n. And 2.042 versus multiplying by 2, 2.07. Again, is this very significant? Probably not. However, if I only took 2 measurements, I'm not even taking 3 for repeatability. I'm just taking 2, and that might happen. Maybe you have a temperature bath. Maybe you have something you can't maybe you can only make 1. If I do that and I use the Welch-Satterthwaite equation, you can see here my coverage factor should be 2.26. If I multiplied everything by 2, I would have a difference of 11.59. So a bit of a difference, just to consider. The more measurements, the better, but measurements are costly. So where you do them and how you do them is going to be up to you. But 11.59% difference between 2 and 5 measurements by not accounting for effective degrees of freedom. This happens more so than TUR, this happens when people do their calibration and measurement capability. A lot of people just multiply everything by 2 at the end. And if you're not accounting for those effective degrees of freedom, your uncertainties could be drastically understated by using that method. So that's a lab beware situation. Why is this all important? If we want to put it together, global consumers risks, JCGM 106, is the role of CPU in conformity assessment is defined as the probability that a non-conforming item will be accepted based on a future measurement result. So we start at SI, go to NMIs. NMIs are good. But what about this company here? That's us. You would hope we're doing things right. Heck, I'm teaching you on TUR. What if we weren't? What happens if we're not taking into account resolution? Then the next tier and the next tier. Look at this. Like, if only one tier of the calibration chain cares about measurement decision risks, then the whole process is at risk. When this risk is propagated throughout succeeding tiers, can we expect the process to work properly? No. Okay, so then we say, okay, Morehouse is doing it right. I trust Henry. He seems honest. So I try to live by that. I don't want to detour and go off, but yeah, that's one of my peeves. I always try to speak my truth, knowing that it can change as I learn more knowledge and whatnot. But we always are very straightforward with people. I do not like people that are not that way. I just prefer not to live my life without being very open and honest. So accreditation, what if they don't do it? You're going to this accreditation calibration service supplier. What if they don't do it? Guess what? What's the risk working? What's the risk in field? If they're not doing it, there's a whole problem. right? It's continual. Yeah, hey, I just saw a question come in. Thank you for the questions. I will address all of these at the end. I didn't say that up front. So if you have them, type them in the question box. We'll stay a little bit later. People can leave when they need to go, but I am more than happy to answer questions. So I painted that scenario where if we keep passing the risk, eventually that risk pass to something we use, to loved ones we care about. Would you want to go on a flight where someone said, "Hey, I'm only testing to 98%. I'm pretty sure the engine's good. 98% sure your engine's good when you're flying in an airplane." If someone told you before you got on that there was a 2% risk that your airplane would fall out of the sky, would you go on that flight? Something to think about. So not as drastic as what we're talking about here, but it does impact everything. So if a calibration laboratory does not include the uncertainty contributors, then they are passing the risk to the customer. Hey, let's not include them. They're hard. We'll just pass it to the next person. Next person could be testing labs where they're not even taking into account uncertainty or doing anything. And then they're insuring something. And that's like Heather started, the bridges we drive on, the hotels we stay in, the planes we fly on, the surgeon's instruments, the medical equipment, all this stuff, right? If we're not making the proper measurements, things have a higher probability of failure. And some things, when they fail, are a pain in the nuisance, and other things are very detrimental. So when you think about something that fails that you bought at the dollar store, probably not too worried if your super glue has the wrong mixture and it still holds for a little bit. But anyway, most likely general industry manufacturer will not calculate the measurement uncertainty associated with their measuring equipment. Although they bear some responsibility, they may not understand their equipment or how to calculate measurement uncertainty. The metrology community has spent decades putting proper measurement uncertainty practice into place. However, the general industry are lagging behind. That is a statement that I find so true. Manufacturers spec something. I just saw it this week. And people say, "Hey, we don't see these things. Are you asking people about them?" Because I think we all can commiserate. Manufacturer specs something at 0.1. Customer buys it. They start making all their measurements. They're 0.7 or 0.07. That's good. That's within 0.01. They start making multiple repeatability measurements. They're 0.14%. They're 0.16, so on and so on. They go back to the manufacturer and say, "Hey, what gives? What did you do?" Manufacturers sometimes are going to say, "Hey, we just took the average." Well, the average hides extremes. Or they're going to say, "Hey, that spec was developed under ideal conditions, which you are not operating at." That is what we hear a lot of. Yes, you are derating the device. They weren't conservative in their specification. They used marketing speak or gospel to sell you a product that now you're thinking you have something that's good to 0.1%. In actuality, probably like 0.15, something like that, just to be aware of it. Again, many in general industry, they're still using outdated concepts such as TUR and traceability. Many in the metrology community have moved away from these terms, but both are still implemented instead of sound. This is what I see with industry. Many do not agree which contributors should be included in the measurement uncertainty evaluation. They argue. It's still being argued. In your labs today, if you go to your quality person, they may not have everything that's in a guidance document. Someone else may say, "Hey, I did this budget 10 years ago. The auditor approved it. I did it 20 years ago. I had this auditor in. I did it 20 years ago. They approved it. I've been using the same budget, not reviewing it." That's problematic. Things have changed. So some argue even that the UUT's resolution does not need to be included in an uncertainty evaluation. However, if uncertainty evaluation does not consider known contributors, there's a question of whether calibration can be metrological, traceable, or accredited. I love this document, LAB 48, but I'm just gonna, if anybody wants to read it, it's UCAS LAB 48. You can make note. It's that's the accreditation body over in England, and they made over in Europe, and they made, since it's UCAS, United Kingdom, but they made a document LAB 48 in which they just ripped apart all these decision rules, and they said when it is and isn't. So what ISO 2017 says, it defines a decision rule as a rule that describes how measurement uncertainty is accounting for when making conformity. So here's where I go off track, and not everyone agrees with me. If you're not accounting for measurement uncertainty properly, meaning simple acceptance or some other things, what is your risk, right? That's really simple acceptance, just using tolerance and not evaluating what measurement uncertainty does to that. That doesn't take into account uncertainty. So that's ignoring it. And then to that end, I like everybody on the line. I haven't met everybody, but I want you all to be safe. I care about you as humans, and I want you to be safe. I'm sure that if we all just decided, oh, red stoplights, I don't like them, I'm going to stop ignoring them. I'm sure if we come back in a month with this group, one of us, at least one of us, are probably going to be in a serious accident if we decide to ignore red stoplights, and we're not going to have the same group of people. It's sad. I like it to a point that it illustrates we cannot just ignore some of the things because they're inconvenient. If we evaluate this in our measuring process, here's Jared. Jared's, he's making a measurement with a caliper and a micrometer with different resolutions. Jared is using a caliper to make a measurement. The drawing specification is 0.005 inches, and the user has a caliper and wants to know if the part is within tolerance. If we sent it off to a lab to be calibrated, they didn't take the resolution into effect, and they said, yeah, it's good. Jared's not going to know. Jared's just going to make a measurement, right? He's going to make the measurement on the part. If the drawing says plus or minus 0.0005 inches, he makes a measurement. If it's in that, he's going to say it's good. Is he ever going to take uncertainty into account in this situation? Would he know to shrink the acceptance limit on the drawing so he can say with little doubt that the part is in tolerance? Or would he grab the micrometer? So over here, those that know calipers, this specification, the reason I use this, is the exact same thing as the resolution on this caliper. So if he calls something intolerance when it reads that at the spec limit, maybe it doesn't fit, depending on what it is. Jared's a great guy. He's our production manager. He would know, because he works here, he would know to go use a micrometer to make this measurement. Lots of people don't know that, or do they supply their staff, their fellow employees with the proper tools, right? So that's a problem. Some end users, they just don't understand the decision rule, what it means for them. Are they comfortable with conformity assessment that does not include all the solutions? In my opinion, they don't know the risks they're subjecting themselves to. A lot of them just want this sticker that says, hey, I just want to know my device is good, and then I can continue to use it. There's a problem with that. And Henry Petrosky, one of my favorite authors, I have many favorite authors, so when I say favorite authors, there's Simon Sinek, there's Adam Grant, there's Stephen Covey, there's John Maxwell is one that's great. And I'm missing so many more. Jim Collins, there's a ton of them. But this guy writes, the role of failure in successful design. I love this line because when we think back to the BP oil spill, when we think back to all the disasters that happen, and you start going the why, if you're familiar with root cause, the why. Failures appear to be inevitable in the wake of prolonged success, which encourages lower margins of safety. Engineers and the companies who employ them tend to get complacent when things are good, worry less, and may not take the right preventative actions. Right? This is what happens. There's complacency. Haven't had a workplace accident, haven't had this, we must be good. The same thing happens with measurements. If we're making, I've talked to people that honestly, I talked to a person that was in doing scales, and they were doing all the scales at their location and then shipping them to other places for use. And I said, well, the gravity's different at other places. How do you account for it? And he was just stymied. He said, you're telling me, if I'm inferring correctly, you're telling me that I've been doing this wrong for 20 years, and I refuse to believe that I've been doing it wrong for 20 years. And I said, well, yes, I am telling you that, and yes, you have been doing it wrong for 20 years. So that's tough. So after learning how to calculate TUR, does anyone else feel that this may describe what is happening in the metrology today regarding the evaluation of risk? You should. Heather posted a link to this spreadsheet. Resolution, if we look at resolution, look, this is a 10,000 pound, 10,000 or 1,000 kilogram load cell. If we start looking at the resolution and what happens, resolution and the effect on risk, as my resolution goes up, so does my risk percentage. On this side, when the resolution is 0.001, insignificant. So here, we're actually looking at the whole standard uncertainty. Resolution's only 0.13%. At 0.01, we're starting to become larger percentage of our overall uncertainty budget. And if we had a 1,000 kilogram device with a 1 pound or 1 kilogram resolution, it would be 99.92. So to say resolution is not significant or cannot be significant is problematic. Statement of conformity. I like this. My favorite line is, if we look at this, here's a small measurement uncertainty. So if you look at this, I'm a Star Wars fan. This TIE fighter looks like it will fly, small uncertainty. I doubt this TIE fighter is going to do much. I haven't seen a large TIE fighter in Star Wars. Probably not going to fly. And why? Because if you look at this, a large percentage is beyond the upper limit, which you're subjecting yourself to a lot of risk. We have this little ad that Heather and I came up with. It's before ILAC G8 in these non-binary decision rules, we were basically dealing with pass-fail. Now, it's a question, right? CalLab 1, the instrument may be in tolerance, but we're not sure. That's if we're not taking risks into account and having the conversations with our customer. CalLab 2 does it. The instrument is out of tolerance, but it still may be okay for your application. Again, these scenarios, what the standard did, it did a good job on a lot of things, but it opened the door, and I don't think it opened any door, so I'm saying that wrong. What it really did is now we're more focused on risk, but people are passing risk to one another, and the recipient does not always know the risk that they are taking or the risk that they have when the Cal Labs use simple acceptance or do not take measurement uncertainty into account. So most people who implement guard bands are using methods found in this handbook. I think that statement should be corrected. This is one that I knew the handbook has the 6 methods. ILAC G8 has methods, and again, that's using guard bands. There's other people using a lot of others, but the handbook has 6 guard bands. Not really going to go into them. I can say I do not like, you'll laugh at this, do not like. Used to think method 2 was pretty good. It calculates end of period reliability. Do not like, do not like, do not like, do not like. I like this one. This is the worst one for calibration labs, but the best one for industry, because guess what? It passes the least amount of risk to you. If you are our customer, it passes the least amount of risk to you. So this is based on the expanded calibration process uncertainty, and it aligns really nicely with the ILAC G8 2009 method. Again, I showed the TIE fighter, so here's what we're saying. Really, if you pick that lab, back to the beginning when I showed you certificates, if you pick that lab with a small expanded uncertainty, there's a lot more room for them to say, when they take uncertainty into account, there's a lot more room for them to make the conformity assessment. If you pick the lab with the smaller uncertainty, maybe you don't know what the scope is, there's a lot less room. This shows it in half. I'm going to show it graphically. So this is calibration process uncertainty. This is our dead weight machines. Remember, 0016. We do the cal, 10,000 pound device. Unit reads 10,008. Man, that's out, right? If you go back to my table, remember, I get like, if I have a 4-to-1 TUR, maybe I have a 75% chance of, but my TUR is 10-to-1. My TAR is 50-to-1. CPK we'll discuss later. I have 0 risk in this scenario, right? So another lab, this is using the ILAC G8 method versus method 5, still 0 uncertainty. It's a little more conservative. Method 6, Morehouse dead weight. Still making a decision to pass. I don't love method 6. Should have removed that slide. But now let's look at the same thing with commercial labs, right? Same measurement, 10,000 pounds. The device is out, has a bias. When I say 10,008, measurement error is 8 pounds. Still out, so it reads 10,008. If I plot this, my risk is now, if I'm not using that standard with a super low uncertainty, I do not have as much of an acceptance limit. Now I pass, if I'm not taking uncertainty, if I'm not using a decision rule like method 5 or ILAC G8, I'm passing 16.53% risk to someone else, and they're going to take it. TUR is 2.4. CPK, not too good. So what happens in a scenario where the lab asks for a TAR of 4-to-1 or some other arbitrary number? Some say, hey, I've evaluated my level of risk, but I have to question if they have. In general, the thought is if the lab performing the calibrations has standards at least 4 times better than what everything is good, is it? It's not. This is a mindset that you have to get out of, and us as a community have to get out of. So our 10,000 pound example, TUR of 3.7, TAR of 4-to-1. So I have a 4-to-1 TAR. My risk is 50%. You know why? Because TAR does nothing, nor does TUR in regard to the location of the measurement. In this scenario, I can have a TUR of a gazillion million, 1,000,000 to 1. Since I'm at the specification line, there is 50% risk, right? You can see this graphically. All of this is risk, 50% of this curve. So if you're going to a calibration supplier and they're doing simple acceptance and you're saying plus or minus 10, they record the reading at 10,010. They say, hey, pass, your device is within specification. It's within the tolerance limit. They've effectively given you 50% risk. And every measurement you make, it's going to continue downstream. And this is where the bad things happen, right? If you do not consider the location of the measurement, you may not be considering risk properly. Here's a scenario, right? Another back to dead weights, really good instrument. TUR 58.7, TAR 62, CPK, total risk. You can look at this measured value. Look how close, since our uncertainties are so low, measured value 10,009.6, and I can still be in. That's basically it. This is telling me at the bottom I could go up to 10,009.825 and still make a conformity assessment. So I talked about CPK, running a little late, but we're wrapping up here. I talked about CPK. It's a statistical tool to measure the ability of process within a customer's specification limits. It's been used in industry for decades. In simple words, it measures producers' capability to produce a product within customer's tolerance range. It's used to estimate how close you are to a given target and how consistent you are to around the average performance. CPK gives you the best case scenario for existing process. So if we're using this CPK, we can see how close the mean of the readings are to the center of the lower and upper spec, how widely spread the readings are. In general, this is process control, but we can use this in calibration because it detects that location of the measurement rather well. If the CPK is less than 1.33, it will need some action. That's at 3 sigma. Different vendor with lower uncertainties, better resolution, adjustments to the instrument, a more repeatable process to make it better. If using 95%, CPK should be better than 1.0, and that's 2 sigma. If the CPK is higher than 1.66, it's likely everything is good. This, for the slide deck, here's how you calculate it. Here's how you use it in Excel if you want to use this tool. Very, very powerful. You can go back and reference it. But I wanted to show the table. So here's 2 sigma. CPK is generally calculated at 3 sigma, and we can use measurement uncertainty. But if we look at this table and where I'm getting my numbers, at 2 sigma, if I use 2 sigma instead of 3, my CPK is 1. I would be at 95.45. 4.55, right? This is the K equals 2 with a K factor of K equals 2. If I wanted to replicate that, not change my formula to 2 sigma for metrology purposes, if I'm better than 0.67, 0.66, I like rounding it up, gives us more room and less risk to pass. But if I'm using 0.67, I can get the exact same thing for a 95.45% yield rate. And as that CPK goes up, so does my yield rate, or so does my risk decrease. Right. So very, very powerful tool. You know, all measurements have a likelihood of calling something good when it's bad and something bad when it's good. Consumers risk, producers risk. PFA is similar to consumers risk. It is the likelihood of calling a measurement good or stating something is in tolerance when the percentage of measurements is bad or out of tolerance. So NCSLI goes on and talks about PFA, 2%, everything else. Don't know if you need to do that anymore. Align with ILAC G8. It's there. It's there to read. So I'm going to get to questions really soon here. False accepts. The importance of this, false accepts can result in reduced end item function or capacity, mission loss, or compromised loss of life. Like I said, I wanted to bring this back. The measurements we make are critical. Damage corporate reputation, warranty expenses, shipping. Do we even know these? Punitive damages. This is a NASA publication, but this stuff matters. It's why NASA measures it, right? If we were just determining quality management system to determine our risk level, how many of you think the NBAs or the accounting departments would be okay with frequent recalibrations? They'd probably push it. Most people, they wouldn't understand this stuff. The entire purpose of analyzing ensure measurements are in tolerance with a risk that's not exceed 2%. It can be whatever. I'm using the numbers from ANSI C540.3, but it could be whatever you've determined your risk is, and why knowing you just have a 4.1 TUR without analyzing PFA regarding the location of the measurement is not enough. Right here's another scenario. I put this just to show it. This says my guard band can be 10,004.83. If I put that in here, guess what? This calculation, I put it in here, it puts me right at the 2% risk. And you can see that in the curve, this little bit that's hanging out. So here's where I ask. Now everybody has information they didn't have before. I ask to please join us in educating the people who underestimate the importance of following the standards, calculating risk properly, using what was presented today. Please, if you get it, get the slide deck, share it. Using what was presented today, you can help us create a safer world by taking a stance to calculate TUR properly.